So, hi everybody. Really appreciate that you stayed until now. I hope I will make your time worth. Okay, so hi, my name is Nimrod Milo. I'm a senior data scientist for Trucks Retail, and today I will talk about one of the latest work that a project that we work on. Which is workforce optimization. And for me, the take-home message that I want to talk about today is data science beyond prediction a bit. So I will introduce a little bit about the company. I'm not sure if everyone knows about Trax. I will also define the problem that we are facing. We'll talk about, let's say, the most common solution approach for this problem. And also I will elaborate more about our approach and our take. So Trax, we are a company that was founded in 2010. The headquarters is in Singapore. The COE is in Tel Aviv. We work in over 45 countries or market in the retail. We work in retail domain. And basically what we do is that we recognize products on the shelf. We have a lot of products that we recognize until now. This is a summary of what we do. Okay, we take a lot of pictures that come from any store, any channel type, anything. A lot of small pictures of the shelf, all of them, we stitch them together, and we allow fine-grained recognition of each individual product that you see here. So this is what the company does. It's a digitization of the physical world of retail. The sources of the picture can be either a sales rep, it could be crowdsourced, it could be a robot, it could be a fixed camera, anything goes, okay? So also, in addition to that, as I mentioned, we are working in over 45 countries, so we have global customers. The customers can be either the manufacturers, what we call CPGs, or the retailers themselves, and of course we have also partnerships with a lot of big companies in addition. So that's just on one leg about Trax. So this kind of operation requires, for us to feed this kind of computer vision monstrosity, we need to feed it with annotated data. So recognition needs annotation. So for us to have annotations at scale in such high demand in almost real time, we need it high available, we need it all the time. We are a global company, everything, we need it like this. We need a back office for this, okay? So recognition requires annotation back office, which this kind of operation requires and raises a lot of challenges. What are the main challenges that we have? We have multiple sites of people working around the world. We have a lot of operational limitations. For example, we need to take care of rights to work. We have a limited office space. We need, the facilities are limited, the amount of computers that we have, network issues, so on and so on. Everything is a limitation, is a constraint. And in addition, we are talking about people. So we have scheduling limitations as well. We need 9 hours consecutive shift. We can't bring someone, let's say, okay, come from home, work 1 hour, then go, and so on. So it's not really a server, of course. It's not on-demand server. We talk about weekly plan. I can tell someone, now you come this hour, now you come that hour, and so on. Breaks, we need night shift, as I mentioned, 24/7. All of this is, we have a lot of business constraints on how to handle this kind of workforce. In addition, we have the constraints and limitation from the side of the business. So from the side of the business, we have several types of annotations. We can have either, working? No? Okay, so what we see here, we can either have, for example, tagging, which means we need to say each one, it is working? Sorry, I'm colorblind, so if it's working, I'm pointing to this side, okay? So never mind. So either tagging, selecting the individual product, or it could be price tagging or voting. For example, we have high quality insurance, so we want to demand high quality from our product and from the results on real time. So we have also what we call a voting process that helps us to check everything is, we give in production high accuracy result. In addition to that, we have limitation of SLA. We have service level agreement, different per project, per customer, even per specific store type. A customer can say, I want this kind of SLA on this store and this kind of SLA on that store and so on. So the limitations are not strictly defined. It's not just a number. And also the data flow comes in surges, in bursts. It's not really something that we can say, okay, all the data arrives together, because some of the data, as we said, comes from visitations in stores. So we can't really go when the store is closed. So we have peak hours and non-peak hours. And we have even sometimes restrictions where the people that collect the data work, for example, in airplane mode. They come at home and then they send all the data, so on. So stuff like that. The data, the flow can vary and be very, very depending on time of day, on day of week, day of month, and so on and so on. For example, someone needs to do 100 visits, so we have a checklist, so they can go in the end of the month, they can do even more visits. So all of that increases the complexity of how the data arrives and how we need to get it and handle it, okay? So that's on that side. And in addition to that, when we talk about how do we want to act as a policy to manage a workforce, we can either say, let's take each person and use their experience in a specific task in a specific project. We can do something else. We can say, let's take one person, for example, the one in blue, and say we want this person to work on all tasks in a specific project. Or the other way, we can say we want the orange one to work on cross projects, but only on a specific task. Or we can have like the green one, which only works on a specific project, on a specific task. So all these kind of limitations are actually the backbone that allows us to have, to meet the different constraints while utilizing the workforce in a better way. Okay? So I hope that until now I managed to show you what Trax does and what are the constraints on handling this kind of workforce. So let's just summarize it as a problem definition in something that we are more familiar with. So in a more data science way, what we want to do, we want to find a policy to meet all back office tasks. We need all of them, while within the SLA, we want to meet the SLA of the customers with minimal resources, because of course what we can say is, okay, give us a bunch of resources, the higher the better, and that's it, but of course it's cost, so we want to remove it. And also, we want to address all of the external or internal constraints that we talked about, the shifts, the limitations, the bursts, and so on and so on. All that stuff, we need to handle it. So what's the typical approach that every data scientist will take? That would say, okay, we have information from the shift, we have the desired SLA, let's take a bunch of features, let's take a bunch of information on the shift, on the flow, daily flow, because we want it weekly, let's look at any feature that we want to add, and we'll try to optimize in a way the SLA and the number of people, QATs. The QAT is Quality Assurance Technicians. That's the resources that we have, what we call QAT. And that's a predictive model, right? So now I have a way to, given a set of features, to predict the amount of QATs that I need to have in a shift while maintaining the SLA. Then, of course, I want to move from the predictive model, because that's what each each data scientist can do, and it's not a problem. It can help you to say what is going to happen. But in this case, we don't want to just to stop there, right? We want to take it to the next step, which is prescriptive modeling. And in this case, what we want to do is to say what needs to be done, meaning how many people do I need to allocate per shift, per project, per task, okay? So the naive approach could say, okay, let's sum the number of resources per shift and get the number of total QATs needed. Okay, so that's one approach. That's the first approach that was taken in Trax, and also from, I can't remember now, another company that I heard that they do a workforce management, and they say, okay, it's working, and it's okay, but it has an issue. The issue is that it's not addressing the fundamentals, limitations, and constraints that we described earlier, meaning that we are failing to capture the relations between the entities or between the lines that we are predicting in the model. Meaning, if we look at the two shifts, let's say that the rectangles are the shift. So let's say I have these two overlapping shifts. The y-axis for the shifts mean nothing. But we can see that both of the shifts overlap in the surge, right, of the data. So because I allocated for each shift individually and I just summed it together, so I say I need 6 QATs for the first shift and 10 QATs for the second shift, which is okay because each one of them said I'm in the surge period, so I need to allocate more people to handle the surge. But the problem is that it could be that I can, for the time of the overlap, I have 16 QATs. It could be that I can reduce the amount of people to 12 or maybe even 10, but still meet the SLA requirements. Okay? And because the way that we build the predictive model and then the prescriptive model, we missed this kind of connection. And the other thing is that we are missing, it's based on the allocation, because we do it on a shift or a project, we miss the experience of the QAT itself, meaning the capabilities that they have. If I want to allocate a specific person and say, this person will work on Nestle or Heineken, how much effort will he give in each project? 50-50, 30-70? It's not clear from the way we model it. And again, if I have something that a person that can work on several projects or several tasks, I miss that relation when I'm allocating on the shift level. So, of course, I can address the first problem by saying, let's move to an hourly prediction and not shift. But again, the problem that I have there is then a shift can't be tracked. It can be removed to 1 hour. I need 9 hours consecutive. Once I bring someone, I need to keep them for 9 hours because this is a shift. Okay? So I break a lot of stuff once I try to enforce it on the model. And that's exactly what happened. We had a model, we saw it working, we saw that we still have too much workforce working per project, and we tried to reduce it, but we kind of got to a limitation that this kind of modeling didn't help. So instead of trying to enforce it on this kind of modeling, we said, let's try to change the approach that we are, the problem itself, the way that we take action, that we look at the problem. So what we did is that we said, okay, the current problem that we have is sequential decision making, okay? Because every time a QAT takes a task from the queue and it does it in time T1 and it finishes it in time it's supposed to be T2, it has an effect, right? It has an effect on the queue. If he does it on T2 or T1, everything is affecting everything else. So the person, what he does in a specific time, how he does it, how much time does it take, everything takes interactions between affects every other entity that we have in our back office. In addition, we have the shift manager. The shift manager only cares about the SLA. The SLA, sorry, I forgot to mention it, it's not computed by each individual task. It's computed by a set of tasks, right? We saw that when I looked at the shelf, we had a lot of pictures, right? I can have one shelf from 20 pictures. I can have it from 50 pictures. I can have it from 100 pictures, okay? So the SLA is not by the individual task. It's more of a group of tasks. So basically what we have here is that not only that the problem setting is sequential by nature, also the reward or the response that we get is not immediate. So it's really hard to do it in a, I don't want to say naive, in a predictive model only, okay? And then enforce the prescriptive model. It's harder to do it like this. But as we can see, this kind of a schema like this really reminds, and we had several talks here today about it, it really reminds of reinforced learning, right? Where we have an agent or a set of agents that takes actions, and the actions affect their situation in the environment, right? And for every action, they get a reward, right? And they want to maximize the reward, and so on and so on. So the setting is very similar to reinforced learning. So what we wanted to do is to say, okay, because we are very close to the realm of reinforced learning, let's take notes and let's look at how to define the problem in a way that it will help us to solve it with methods from reinforced learning. So when we look at reinforced learning, one of the key elements that, that each reinforced learning algorithm relies on is the environment, right? Because we need to model an environment for it. If the talk that was earlier before, we want to simulate a self-driving car, right? So we need to simulate it, right? So the environment is the simulation. So there are a lot of out-of-the-box simulations for key tasks. So if I look, for example, on OpenAI Gym, it helps us to train agents on various tasks, from walking to playing games like Pong or pinball. We have Deep Drive, which is a simulation for experimenting with self-driving AI. We also have SRL Toolbox, which is a toolbox for robotics. It's an extension of OpenAI. It helps to give either simulation for specific robotics with hand, with arms, and so on. So it extends OpenAI Gym. But for us, we have a problem. We need to learn an environment for us, because for our domain, we don't have such an environment. So this is exactly what we did. We built our own environment, and this is what I want to show you for the rest of the talk, how we treated and how we built such an environment for us. It was actually quite easy once we got our head around the idea that we need to model it as a simulation. It was very straightforward for us. What we did is that we took the approach of simulating the back office behavior as close to reality as possible. That's our goal, okay? How do we want to do it? We want to look at our agents or our active players in a simulation. So for us, a player could be a QAT, a shift manager, and an inflow controller. Okay, so those are the three agents that we have. How did we model each one of them? Let's take a deeper dive. So to model the QAT, we wanted to, because the simulation must be stochastic, right? We don't want a simulation that will run exactly the same all the time. We need to add noise, we need to add randomness, of course, because otherwise it will be boring, right? I know exactly what will happen. It doesn't help in any way. So what we did is that we model each one, almost each one of our agents as a random variable. So as a QAT, when we looked at the QAT, what we did is that we generated a simple histogram to see for a specific task how much time what's the average, what's the distribution of time it takes for QATs to do this specific task. Okay? Once we got this, another note, the reason why we wanted to look only at the time is that because when we look at the computation time itself, implicitly, we take into account the complexity of the task. If a task have, an image has 7 products or 70 products, the reason, our assumption is the time will be higher for 70 products than for 7 products. So when we look at the time, we take into account implicitly, the hardness of a task. But because we wanted a random variable, we said, okay, we can't really look at the histogram and sample from it. It's kind of boring. So what we did is that we took 2 approaches to feed the data. One is that we used a generative model. We used a KDE, which we can see here in the in the green line. I hope you can see it. This one. As we know, KDE smooths the data, so we can see it's a little lower. The other method that we used is we used maximum likelihood to locate the actual distribution. And once we learned the distribution and its parameter, we chose, of course, the most fitted one. We did a competition. It's very standard between a lot of distributions. So we did it. We can see that the distribution actually learns the data in a better way. We can see that near the top, it actually catches the data in a more granular level. So this is the approach that we took for the QAT. For the inflow controller, which is a little more complex, we wanted to collect data per project, per project, and also we wanted to look at it as a random variable. The problem is that we have the inflow, we said it can arrive to a lot of different places from a lot of different geographies, so we wanted to normalize everything. So of course we took everything to UTC, but in addition to that we wanted to look at what we call time T0. So we arbitrarily select T0 to be the start of the first shift in all in all the back offices that we have. In this way, we have everything normalized to a specific time. Okay, just for us to see it. And you can see that the data looks, the search looks very similar to the one that I showed you before. And again, because the SLA computation is comprised from a set of tasks, we needed also to model the amount of tasks per visit that we have, and also the arrival rate, right? Because when I take a picture, it takes time until it's uploading, right? Okay, so every time I take a picture, the arrival rate also I need to take into account. Just a small anecdote. You can see here that actually KDE failed to fit the data miserably. It's the green on the bottom. That's the KDE. When I try to fit it to the arrival rate, on the contrary, when I used log norm to fit the data, it captured the data better. In the peak, it's not perfect, but it's much better than the KDE. That's the reason why I always take the 2 approaches. Each one of them helps in different times. So this is what we did. So again, Emily helped us, came to the rescue. The shift manager, it's actually the most simple one. It's just someone that enforces the policy. He adds a QAT to a specific shift. Okay, so this is the agent that adds the QAT to the shifts and, of course, tell them when to go off. And also, we added capabilities of controlling the brakes. So again, the brakes we modeled as a random variable. So, of course, we didn't really rely on the simulation, even though I wrote it. So what we did is we verified it. We verified it in a very simple manner. We just ran historical data, and we observed the actual versus the simulation results. We can see that there are fluctuations, and of course, it's not perfect, but it captured the gist of the situation. Okay? And now, putting it all together, this is the fun part. We used a package called SimPy, which is a simulation for Python. It's very easy, very nice. The entire code was 80 lines with comments, actually. Of course, not the fitting. The fitting is, let's say, 100 more of all the data. I think the SQL queries are the longest, without a doubt. So everything was really perfect, really short. And that's it. If you have questions, thank you very much.